In last lecture, we discussed about the inductance. We defined inductance as the total flux per unit current linking a particular coil. In other words, inductance was defined as N phi divided by I, that is, it gives us the measure of the flux per unit of current established in a coil. Next, we discussed that inductances are of two types. One is known as mutual inductance and another one is known as self-inductance. In mutual inductance, the current is flowing in one coil and we are measuring the flux in another coil. That is, mutual inductance is defined as the flux linking a coil per unit of current flowing in another coil. For example, we define mutual inductance of coil 1 with respect to coil 2 as the total flux linking coil 1 per unit of current flowing in coil 2. And we define self-inductance of coil, say C1, as the total flux linking the coil per unit of current flowing through the same coil. From the discussion in the last lecture, there are three useful formulae that we need to remember and carry it forward. First one is this: N phi, that is total flux through a particular coil, is equivalent to inductance, which is a constant. It depends upon the geometric configuration and orientation only, into current I, that is total flux N into phi B is equivalent to inductance L into current I. We have an expression for mutual inductance of coil 1 with respect to coil 2. Mutual inductance will always be between two coils. Mutual inductance cannot be of a single coil because it is mutual inductance of one coil with respect to another coil. Current has to be flowing in some another coil. Whereas self-inductance is of a single coil. You have a single coil, it has a self-inductance, that is total flux per unit of current flowing through the same coil. Whereas for mutual flux, we have total flux through a particular coil per unit of current flowing in some another coil. Fine? Okay. Now let's try to derive expression for mutual inductance. Of a simple configuration. Of a simple configuration. Now let us suppose we have two coils. Which are concentric. Suppose this is coil 1 and there's the larger one. Suppose this is coil C1, this is coil C2. This coil C1 has N1 number of turns. Coil C2 has N2 number of turns. These are concentric. That is, their axes coincide. Two solenoids. We have two solenoids here. Which are placed in concentric manner. Coil C1 or solenoid, let's call this solenoid S. Solenoid S1 and solenoid S2. Solenoid S1 has N1 turns, solenoid S2 has N2 turns. Let's suppose length of both the coils L is same. Also let small n1, you remember small n1? We used small n to represent number of turns per unit length. So small n1 is number of turns per unit length of coil S1 or of our solenoid S1, whereas n2 is number of turns per unit length in solenoid S2. Also, let R1 be radius of solenoid S1 and R2 be radius of solenoid S2. Fine. What we want to calculate here is, we want to calculate the mutual inductance of coil 1 of solenoid 1 with respect to solenoid 2. Similarly, we want to calculate the mutual inductance of solenoid 2 with respect to solenoid 1. Have a look how we will approach this problem. Let us suppose I2 current is flowing or is set up in solenoid S2. We will initially assume there is no current flowing through this solenoid S1. Current is only flowing through solenoid S2, the one with the larger radius R2. Because of the current flow through solenoid S2, solenoid S2 will produce a magnetic field, where you already know this from the chapter magnetic field, that B is equal to mu naught Ni, small n. When current I2 is flowing through solenoid S2, it produces a magnetic field B2. When solenoid S2 produces a magnetic field, that means it produces a magnetic flux. Try to concentrate here. That magnetic flux will be here inside the solenoid. You remember this? Inside the solenoid, magnetic field is constant and parallel to the axis. So magnetic field or magnetic flux because of this solenoid S2 will be parallel lines here. Since solenoid S1 is placed inside solenoid S2, therefore a part of flux will also pass through S1, because flux is passing through this inside solenoid S2, and solenoid S1 is placed inside solenoid S2, so flux, some part of flux will also pass through, will also link solenoid S1. Fine. Now how much flux will link solenoid S1 because of current in solenoid S2? If current in S2, that is I2, if current I2 is large value, so its magnetic field will be stronger, so its flux will be more. When its flux will be more, so flux linking this solenoid S1 will be more or less, it will be more. That's what we have discussed till now, that total flux linking solenoid S1 N1 phi 1 is directly proportional to total flux linking solenoid S1 is directly proportional to current I2 that is passing through solenoid S2. More the current in solenoid S2, more the flux through S2 and hence more the flux through S1 also. So flux, since we want to calculate flux through S1, so flux through S1, that is N1 phi 1, is directly proportional to I2. From last lecture we also know, since we are calculating flux through coil S1 because of current in solenoid S2, this is the case of mutual inductance. So here constant of proportionality will be phi 1 will be equal to mutual inductance M, where we are calculating mutual inductance of 1 with respect to, since current is flowing in 2, with respect to 2 into current I2. Let me remind you what we basically want to calculate out of this is, we want to calculate the mutual inductance between the coils. We want to calculate the expression for mutual inductance for this configuration. Remember, the expression that I will derive here is not the mutual expression for a general expression for mutual inductance in all the cases. No, this is expression for mutual inductance for this configuration of solenoids or for this configuration of two coils. Now tell me, this N1 is number of turns in solenoid 1, phi 1 is flux through solenoid 1, M12 is mutual inductance of 1 with respect to 2 that we want to calculate, and I2 is current flowing through solenoid 2. Can I express this flux passing through coil 1? Do we have an expression for phi 1? Since we already know that flux phi anywhere is equivalent to flux density, what you call as magnetic flux density B into area A. Fine. This phi 1 is flux that is passing through solenoid 1. But this flux basically that is linking solenoid 1 is produced because of current in solenoid 2. So this B magnetic field, this magnetic field B will be magnetic field produced by solenoid 1, or this will be magnetic field produced by solenoid 2. This will be magnetic field produced by solenoid 2. Though this flux phi 1 is the flux that is linking coil 1, but the flux that is linking coil 1 here is because of the magnetic flux produced by coil 2. So we write here this as N1. The flux that will link this, so coil 1, is because of the magnetic flux density B because of coil 2. So this will be, this phi 1 will be replaced by B2 into this flux is passing through which area? This whole area we want to calculate flux through this area. We want to calculate flux through area of coil 1 into A1 is equivalent to M12 into I2. Please don't confuse yourself. I will repeat this once more here. Total flux, we want to calculate total flux N1 phi 1 through coil 1. Total flux N1 phi 1 through coil 1 flux through coil 1 will be equal to what is the magnetic field over there and area of the coil. This is like, say for example, this is a coil. I'm drawing here this S1, N1, small n1 and R1 coil. It's given that magnetic field here is B and area here is, magnetic field here is B2, area here is A1. What is flux through this coil? Flux through this coil is magnetic field here. What is magnetic flux density here? Which is the external magnetic field. What is the magnetic flux density here? Is magnetic flux density here because of solenoid S1 or S2? It is because of S2. That's why I represent it here as B2. So magnetic flux density here is B2. And the flux passing through this coil, let's call that as phi 1. That flux phi 1 will be equal to external magnetic flux, then that is B2, into area of which coil? Area of this coil, area of this coil. We want to calculate flux through this coil. Its area is A1, so B2A1. That's why I mentioned here as B2A1. So we can write this as N1. This B2 is magnetic flux density because of solenoid 2. We already know expression for magnetic flux density because of solenoid, that is mu Ni. So mu naught, this is B2, so this is N2, number of turns per unit length of solenoid 2 into current I2. Then A1, that is area of the smaller coil through which we want to calculate the flux. The flux through this coil, the area A2 of solenoid S1 is pi R1 square will be equal to M12 into I2. Also, this N1 is total number of turns of solenoid 1. We can also represent this N1 as, since we know N1 is total number of turns of solenoid 1 is small n1, number of turns per unit length of solenoid 1 into L, length of solenoid. So I will represent this as small n1 L mu naught N2 I2 pi R1 square is equivalent to M12 I2. I can cancel this I2 with this I2 and I can obtain expression for mutual inductance M12. So from this you have M12 mutual inductance of 1, that is flux passing through coil 1 because of current in coil 2, that's what we have calculated, is equivalent to, this is mu naught, then we will write this N1, then we will write this N2, then we will write this pi, then R1 square, then L. This is expression for mutual inductance of coil 1 because of current in coil 2, that is mutual inductance of coil 1 with respect to coil 2. Let's now calculate the opposite, that is, now I want to calculate what is mutual inductance of coil 2 because of current in coil 1. I want to calculate M21. Mutual inductance of coil 2 with respect to coil 1. I will again begin in similar fashion. We already know that, now assume there is current I1 flowing through solenoid S1. let I1 is set up in solenoid S1. I1 is set up in solenoid 1. Now what is the flux that will link solenoid S2? We'll call that N2 phi 2 will be directly proportional to current I1. More the current here, more will be this magnetic field, more will be its flux, and more flux will link solenoid S2. Or we can write this as N2 phi 2 is equivalent to M21 I1, where M21 is mutual inductance of coil 2 with respect to solenoid 1, or solenoid 2 with respect to solenoid 1. Again now here, concentrate a bit here. This is N2 phi 2. What is phi 2? Phi 2 is the flux that is passing through coil S2. But current is only now flowing. Now there is no, we are assuming there is no current in S2. Current is only in S1. When current is only in S1, it will produce a flux. That flux will pass through S1. It will flow something like this. It will come back through here. If I ask you what is flux through coil S2, you can see it from the figure. That flux through S2 is only confined to the area of coil, this much of area equal to that of coil S1. What I want to convey here is the flux phi 2. The flux phi 2 that is passing through coil or solenoid S2, flux is only flowing through this much part, this area only. There is no flux here. Why? Because current is flowing through solenoid S1 and solenoid S1 is into solenoid S2. When the flux is being produced by solenoid S1, it passes through solenoid S1, it will definitely pass, and then it will come from here, because these field lines try to be as far apart as possible, we know that. So we'll write N2 into, what is phi 2 now? Phi 2 is flux through solenoid S2. Flux phi is B into A. Here B is because of B is magnetic flux density that is produced by S1. So here you will have B1. Now here you have to understand this. Here I took area A1 because whole of the area A1 was being linked to the flux. Flux was passing through whole of this area A1. But here in this case, is whole of the area of S2 being linked with the flux? Or in other words, is flux passing through whole of the area? Or is flux passing through this much area equal to A1? Flux is passing through this much area only, A1. So this is B1, A1. Is equivalent to M21 I1. I hope you got this. Why it was here B2A1, but here is B1A1. It's not here B1A2. Why? Because flux is not passing through the whole area A2. It's only passing through area A1. Because once flux reaches here, it won't come from this path. It comes from outside. Because flux lines tend to be as far apart as possible. So there's N2, B1, A1. So you know expressions, value for these expressions. This is N2. What is B1? This is mu naught N1 I1. How much is A1? This is pi R1 square is equivalent to M21 I1. This I1 will go with this I1, so we'll have expression for M21. Mutual inductance of 2 with respect to 1 is equivalent to mu naught. Similarly, I can replace this with N2L. So we can write this as first this N1, then this N2, then pi, then R1 square. I have replaced this N2 here by N2 into L. So mu naught here, then N1, then N2, then pi, then R1 square, and finally L. This is expression for mutual inductance of coil 2 with respect to coil 1. Let's have a look between the two. Here M12 is mu naught, N1, N2, N2, pi, R1 square, L and L. Thus we concluded that mutual inductance of coil 1 with respect to 2 is equivalent to mutual inductance of coil 2 with respect to coil 1. Mutual inductance of 1 with respect to 2 is equivalent to mutual inductance of 2 with respect to 1. Though we have derived this for a simpler configuration of two coils, which are concentric, but this expression holds in general. This actually directly comes from the common sense as well. I'll come to it in numericals as well. One more thing. This is expression for mutual inductance when the two solenoids are placed in air. If the two solenoids are not placed in air, they are placed on some ferromagnetic material of relative permeability mu r. So in general we can write M12 is equivalent to M21 is equivalent to, it will become mu naught mu r, this is the additional term now, N1 N2 pi R1 square into L. Now, you could have observed one thing here. If you remember, when we derived the expression or when we wrote the expression for resistance R, that was equal to rho L by A. When we wrote expression for capacitance or parallel plate capacitor, that was epsilon naught, epsilon R if dielectric material is inserted in between, A divided by D. Resistance of a material or resistance of a resistor depends upon the geometric dimensions, length, area and the material. Does resistance depend upon current? No. Does resistance depend upon voltage? No. Similarly, when we derived expression for capacitance, capacitance depends upon area of the plates, distance between the plates and the material in between the plates. Does capacitance depend upon voltage? No. Does capacitance depend upon current? No. Now when we have expression for mutual inductance, this also does not depend upon current or voltage. Do you have anywhere value of current in the expression? No. Voltage in the expression? No. So mutual inductance like resistance and capacitance also depends upon geometry or you can say dimensions. Geometric dimensions. It depends upon length, it depends upon radius, it depends upon number of turns. All other things are constant. In addition to this, mutual inductance also depends upon the orientation. I touched this in last class as well. Suppose we have these two coils and this is one configuration A. Suppose this is configuration B. This is one coil, this is second coil. Is mutual inductance here more or is mutual inductance here more? Now you know mutual inductance is how much flux of one coil is linking the another coil. Does here flux link more or here flux link more? Flux links here more. In fact, here mutual flux M12 is almost equal to 0 because no flux of this coil links this coil. Here, mutual inductance is a fairly large value compared to this. So you'll remember this, that mutual inductance depends upon the geometric dimensions and the orientation of the two coils. Fine? We'll continue our discussion in next lecture. Thank you.